Thank you for giving me opportunity to say something in PVSec 30 and GBPC 2020. Today my topic is impact of oxygen fluoride on properties of CO4O3 thin films fabricated by radio frequency sputtering. I am Abdul Majed Patwary. The other co-authors are listed here. This work is a collaborative work in between Saga University, City University of Hong Kong, Lawrence Berkeley National Laboratory, University of California, and Kumilla University. Background of my study. Paramelaconite was discovered in 1870 in a copper queen mine at Arizona, USA. This material is very interesting, abundant and low cost, eco-friendly. It has p-type conductivity with high absorption coefficient. Theoretical energy conversion efficiency is around 29%. In this slide, the crystal structure of CO4O3 is represented with the crystallographic properties of CO4O3. CO4O3 is basically a body-centered tetragonal cell, and its lattice constants are A equal to 5.837 Armstrong, whereas C equal to 9.88 Armstrong, atomic ratio 1.33, cell volume 338 Armstrong cube, and density 5.93 gram per cm cube. Here I introduce the theoretical Shockley-Quasiel limit for different materials. If we see the graph, we will find that in case of CuO, its band gap is 1.4, so the theoretical energy conversion efficiency is around 30%. In case of Cu2O, band gap energy 2.1, so the Shockley-Quasiel limit shows that the theoretical energy conversion is around 20%. On the other hand, in case of CO4O3, its band gap 1.5, so the theoretical energy conversion efficiency is approximately 29%. We also introduced the first ever done CO4O3 based solar cell done by Mayer et al. Its energy conversion efficiency is low, only 0.009%. We already studied the deposition condition of 3 copper oxide and optimized the growth condition for CO4O3. To utilize CO4O3 thin films in optoelectronics, we have to control the electrical properties of CO4O3, and to do so, we have to control the deposition parameters like substrate temperature, oxygen flow rate, sputtering pressure, or power. So in this study, we want to study the effect of oxygen flow rate on CO4O3 thin films. And so the motivation of this study is to understand the effect of oxygen flow rate on properties of CO4O3 thin films. So here we can see the schematic view of RF sputtering system. If we see the inside view of the chamber, we will find that substrate heater is in the upside, and the 3 target can be used here. I use copper target and the gas inlet, the exhaust, and the substrate heater and the target is 80 millimeter apart. I also introduced the experimental conditions. The background pressure of the chamber was 3 into 10 to the power minus 4 Pascal, RF power 50 watt, deposition time 1 hour. Substrate temperature is maintained at 300 degrees C. Argon gas flow is constant at 10 SCCM. Oxygen flow rate is variable in between 0.82 to 1.06 SCCM. Sputtering pressure is 1.8 Pascal. We use sapphire substrate and the size is small, is 10 into 5 into 0.5 millimeter cube. Then resultant discussion. The XRD patterns and Raman spectra of CO4O3 thin films are represented here. If we look at the XRD patterns, we will find that from 0.86 to 1.00 SCCM of oxygen flow rate, only single phase of CO4O3 can be detected. If we increase the oxygen flow rate to 1.06 SCCM, we will find peaks from CuO single phase. If we decrease the oxygen flow rate to 0.82 SCCM, we will find mixed phase of Cu2O and Cu4O3. Similar result can be found by Raman spectra, like from 0.86 to 1.00 SCCM, Single phase of CU4O3 can be detected from the fix of Raman like 328, 531 and 640. And if we increase the oxygen flow rate to 1.06, we will find fix from CuO, and if we decrease the oxygen flow rate to 0.82, we also find fix from mixed phase of Cu2O and Cu4O3. Therefore, the windows for Cu4O3 is very narrow. Oxygen partial pressure of 7.9 to 9.1% is required to get single phase of Cu4O3. We also measure the grain size by Sekab formula. The highest grain size is 34 nanometer at oxygen flow rate of 0.90 ccm. In this slide, the resistivity, carrier concentration and mobility of Cu4O3 thin films are represented. If we look at the resistivity and oxygen flow rate, we will find that the resistivity decreases from 978 to 242 ohm centimeter with a slight increase of oxygen flow rate from 0.86 to 0.90 SCCM. If we look at the Hall concentration, we will find that Hall concentration decreases from 4.5 into 10 to the power 18 to 2 into 10 to the power 16 per cm cube with increasing oxygen flow rate from 0.90 to 1 SCCM. Moreover, an increase of oxygen flow rate from 0.86 SCCM to 1 SCCM also results in an increase of Hall mobility from 0.01 to 0.25 cm square per bs, which is the highest mobility reported so far. Murali et al. Reported the mobility of only 0.04 cm square per bs. Although the intrinsic p-type conductivity is typically attributed to a spontaneous Cu vacancy formation during the growth of Cu4O3, this appears to be inconsistent in our observed reduction of the Hall concentration with increasing oxygen flow rate. However, a similar increase of Hall concentration with increasing oxygen content in p-type CuO films was reported. Temperature dependence of resistivity of thin films can be calculated by Arrhenius model of resistivity like rho equals to rho naught exp minus Ea divided by kBt, where rho is the resistivity of the material, T is the temperature, and Ea is the conduction or thermal activation energy. In this slide, the temperature dependent resistivity, mobility and carrier concentration for samples grown with oxygen flow rate of 0.96 and 1 SCCM in the range of 190 to 570 Kelvin are shown as Arrhenius plots. As shown in figure, two conduction activation processes can be observed for low temperature range of lower than 400 Kelvin and high temperature range of higher than 400 Kelvin. Two activation energies can be extracted from Arrhenius plots, and a conduction activation energy Ea1 of around 0.21 electron volt is found at low temperature for both Cu4O3 thin films. On the other hand, the conduction activation energy Ea2 at high temperature is different for the two samples with the different oxygen flow rate. The high temperature conduction activation energy Ea2 for the two samples grown with oxygen flow rate of 0.96 and 1.00 SCCM are 0.29 electron volt and 0.43 electron volt respectively. As shown in figure, the increase of conduction activation energy is predominantly associated with an increase of mobility in the high temperature range 380 to 570 Kelvin. Interestingly, the Hall concentration shows a similar temperature dependence for both films with a single thermal activation energy of Hall Ea3 of 0.12 electron volt in the whole temperature range. This can be taken as ionization energy of acceptors. The thermal activation energy of Hall Ea3 is similar in both of the Cu4O3 thin films, which indicate that a similar acceptor is expected to exist in these samples. Since copper vacancy is believed to be the origin of the acceptor in copper oxide, similar copper vacancy may exist as acceptors in these flames. Optical absorption spectra of CuO4O3 and CuO thin flames synthesized at several oxygen fluoride are shown here. Here in the table, we also show the optical bandgap energy obtained by different tau feeds like direct allowed, direct forbidden, indirect allowed with respect to oxygen fluoride. If we look at the graph, we show that the large absorption coefficient of higher than 10 to the power 4 per cm suggests that CuO4O3 has a direct allowed transition. The inset of the figure shows plots of alpha h nu square for the same samples as a function of photon energy. For the CuO4O3 thin flames synthesized at oxygen flow rate from 0.86 to 1 sccm, the spectra show an optical band gap of 1.52 to 1.62 electron volt. In conclusion, we can say that the structural, electrical, and optical properties of single phase of CuO4O3 as a function of oxygen flow rate were measured. A very narrow window of 7.9 to 9.1% oxygen partial pressure was required to group few CuO4O3 thin flames. The highest mobility of the flame was achieved to 0.25 cm square per bs, which is the highest reported value so far. The lowest resistivity of the flame was 242 ohm centimeter, and all the flames show p-type conductivity. CuO4O3 flames demonstrated a high absorption coefficient with a direct transition at 1.52 to 1.62 electron volt. These outcomes show that CuO4O3 is an affiliate material for photovoltaic and optoelectronic device. Thank you for listening to me. Thank you very much to the all organizer of PVSEC 30 and GPVC 2020. Thank you very much.